Welcome back to the Deep Dive. Today, we're heading out, way out, to our closest neighbor in space, the Moon.
That's right.
We're going to cover, well, pretty much everything, from how it got there in the first place is a really dramatic origin story, all the way to what we're planning next. You know, building bases, maybe even spaceports. We've got some great sources lined up for you.
Yeah, it's going to be fascinating because the moon isn't just a rock in the sky. It's fundamental. It helps us understand Earth. It's potentially key to life here, and it really is our next big step out there.
Our next frontier.
Exactly. So our mission today, if you like, is to dig into how it formed, how it affects us right here on Earth, the missions we've sent, and what this future on the moon might actually look like.
Okay, let's unpack this. How did the moon form? The big theory, the one most scientists are behind, is the giant impact hypothesis, right?
That's the one. The idea is way back, early Earth got slammed by something huge.
Huge.
Like another planet, roughly the size of Mars. We call this hypothetical body Theia.
Theia, okay.
And this collision was just immense. It would have blasted a huge cloud of vaporized rock and debris into orbit around the young Earth.
And that debris eventually clumped together to form the moon.
That's the core idea. Over time, gravity pulled all that material together. It's quite a violent birth story.
It really is. And what's the evidence? How do we know this isn't just a, cool story?
Well, there are several strong lines of evidence. First, the way the moon orbits Earth, it's quite similar to Earth's own rotation and its path around the sun. That suggests a shared energetic origin.
Okay, that makes sense.
Then there's the chemistry. When we look at rocks from the moon, brought back by Apollo missions, and compare them to Earth rocks, their stable isotope ratios are basically identical, indistinguishable.
Wow, so they're made of the same stuff.
It strongly implies they formed from the same well-mixed batch of material, which fits the idea of a giant smash-up mixing everything together. Also, the Earth-Moon system spins faster. It has more angular momentum than you'd expect for a planet-moon system formed differently. A giant glancing blow could easily provide that extra spin.
Ah, okay. Like cosmic billiards?
Sort of. And we know the moon was once largely molten, a magma ocean. That requires a huge amount of energy.
Which a giant impact would definitely provide.
Exactly. Plus, the moon has a tiny iron core compared to Earth. The models suggest Theia's iron core mostly merged with Earth's core during the impact.
Leaving the moon to form from the lighter outer layers.
Primarily, yes. And finally, the moon is missing a lot of volatile elements, things that vaporize easily. They likely boiled off in the intense heat and escaped the moon's weaker gravity.
Okay, that sounds like a pretty solid case. But science is always refining things, isn't it? Are there still questions or tweaks to this main theory?
Oh, absolutely. While the giant impact is widely accepted, the exact details are still debated. There are subtle compositional things that the basic model doesn't perfectly explain.
Like what?
Well, things like the precise ratios of certain elements, or the surprising discovery of some water trapped in lunar volcanic glasses. How did that survive?
Good point.
So there are refinements. One idea, the equilibration hypothesis, suggests Earth and the debris disk shared a common silicate vapor atmosphere right after the impact, which would really homogenize the isotopes.
Okay, like a shared steam bath of rock vapor.
Pretty much. Another is the synestia hypothesis. It suggests the impact made the Earth spin incredibly fast, forming this weird donut-shaped structure of vaporized rock called a synestia.
A donut Earth. Seriously.
For maybe a century or so, yeah. Until it cooled and condensed into the Earth and moon we see today. That could also explain the isotopic similarities.
That's wild.
And these models are trying to grapple with really fine details, like the moon's iron oxide level, which is sort of intermediate between Mars and Earth, or why the oxygen and titanium isotopes are so incredibly identical. It pushes our understanding.
It really shows how complex figuring out cosmic history is. Okay, so this violent beginning gives us our moon. Let's talk about its effects here. The most obvious one is tides.
Definitely the most visible. The moon's gravity pulls on Earth's oceans,
creating a bulge on the side facing the moon.
Right, but it also pulls the solid Earth slightly away from the water on the far side so that water gets left behind, forming another bulge.
Ah, so two bulges.
Exactly. And as Earth spins underneath these bulges, most coastlines experience 2 high tides and 2 low tides each day. Well, each lunar day, which is about 24 hours and 50 minutes.
That constant pull.
Yeah.
It must have longer-term effects, too, beyond just the daily tides.
Oh, absolutely profound effects. That tidal friction, the sloshing of oceans, actually acts like a brake on Earth's rotation.
Slowing us down.
Yep. Very, very slowly. Our days are getting longer by about 1.7 milliseconds per century. Doesn't sound like much, but over geological time,
It adds up.
it really does. We have fossil evidence from ancient mollusks about 70 million years old showing Earth had 372 days in a year back then. The days were shorter.
Wow. And if Earth is slowing down, where does that energy go?
It gets transferred to the moon. As Earth loses angular momentum, the moon gains it.
And that means
It means the moon is slowly moving further away from Earth by about 3.8 centimeters or 1.5 inches per year.
it's drifting away.
Slowly but surely. But perhaps the most critical effect, the big picture one, is climate stability.
How does the moon affect climate?
It stabilizes Earth's axial tilt, our obliquity, the angle that gives us seasons.
Right, about 23.5 degrees.
Exactly. Without the moon's gravitational influence, calculations show Earth's tilt could wobble chaotically, maybe varying anywhere between 0 and 85 degrees over long time scales.
85 degrees, that would be catastrophic for climate.
Utterly. Imagine the poles pointing almost directly at the sun sometimes. It would lead to extreme, unpredictable climate swings. Our moon keeps that tilt relatively stable, just varying by about plus or minus 1.3 degrees around the current value.
So the moon is like Earth's stabilizer wheel.
A crucial one. Look at Mars. It has only tiny moons, effectively none for stabilization, and its axial tilt varies wildly between 0 and 60 degrees. That's likely a major factor in why it's so barren today.
That really puts the moon's importance into perspective. And it affects life, too, not just geology.
Oh, for sure. Many birds navigate using moon phases. Lots of coastal creatures time their feeding and reproduction to the tide.
Like the coral spawning.
Exactly. The mass spawning on the Great Barrier Reef is famously synchronized with the full moon. It's all interconnected.
Incredible. Okay, let's shift to us humanity looking at the moon and then going there. We started with robots.
We did. The space race kicked things off. The Soviet Union got there first with Luna 1 doing a flyby in '59.
Just a flyby.
Yep. Then Luna 2 actually impacted the moon later that year. First artificial object to reach it. They followed up with the first soft landing, Luna 9 in '66, and the first orbiter, Luna 10, also in '66. They really pioneered robotic exploration early on.
And the U.S. and others followed.
Yes, the U.S. had missions like Ranger, Surveyor, and later Lunar Orbiter mapping the surface. Then came missions like Clementine, Lunar Prospector, Europe's Smart 1, Japan's Selene, India's Chandrayaan 1, all building up our knowledge robotically.
But then came the moment everyone remembers. Apollo.
Apollo, yeah, that was the game changer for human exploration. President Kennedy's challenge in '61.
To land a man on the moon and return him safely to the Earth.
Before the decade was out, it was an immense undertaking. You're talking 400,000 people, 20,000 companies working on it.
It's just staggering.
And the achievements were monumental. Apollo 8, Christmas Eve 1968, first humans to orbit the moon, seeing Earth rise.
An iconic image.
Then, July 1969, Apollo 11. Neil Armstrong takes that one small step.
Unforgettable.
By the end of the program in 1972, 6 missions had landed 12 astronauts on the moon. They brought back 842 pounds, that's 382 kilograms of rocks and soil.
Which completely changed our understanding of the moon's geology.
Absolutely. We learned about the ancient highlands, the volcanic plains, the impact history. It wasn't without tragedy. Of course, the Apollo 1 fire led to crucial safety redesigns. But the engineering, the Saturn V rocket, the lunar module, it was incredible. And having a geologist, Harrison Schmitt, on Apollo 17 was key.
And now, lunar exploration seems to be booming again.
It really is. We've seen recent successful landings by India with Chandrayaan 3 in 2023, Japan with SLIM in 2024, and SLIM impressively survived several lunar nights.
That was amazing.
And just this year, 2024, the first commercial lander, IM-1, made it down.
It feels like a new era. China's program is also very active.
Very ambitious. The Chinese Lunar Exploration Program, or CLEP, they've had orbiters, landers, rovers. Chain 4 was the first ever landing on the far side.
The far side. Always hidden from Earth.
Exactly. And they've done sample returns, Change 5, and just recently, Change 6 brought back samples from the South Pole Aitken Basin, a huge ancient impact crater. That's incredibly valuable science.
Which brings us to NASA's current big program, Artemis.
Artemis. The goal is sustained human presence, this time with international partners under the Artemis Accords. It's framed as Moon to Mars.
So what's the plan?
It's phased. Artemis 1 was the uncrewed test flight of the big SLS rocket and Orion capsule back in late 2022. That went well.
I remember watching that launch. Impressive.
Artemis 2, currently aiming for maybe April 2026, will be the first crewed flight, looping around the moon, taking humans farther than ever before.
And then the landing?
Artemis 3, targeted for mid-2027 perhaps. That's the plan for the first crewed landing since Apollo 17, aiming to put the first woman and the first person of color on the moon.
A historical. And there's this gateway concept, too.
Right, the Lunar Gateway. Think of it as a small space station in orbit around the moon. Not permanently crewed, but a place astronauts can stop, resupply, assemble missions.
Sort of staging post.
Exactly. A hub for missions down to the surface and potentially further out into deep space. It relies heavily on international collaboration. Canada's building the robotic arm, for instance. It uses efficient solar electric propulsion to move between orbits.
So all this activity leads to the idea of a permanent base. What was that actually involve? Why build one?
Well, a permanent base moves us beyond short visits. It allows for long-term science, like astronomy from the moon or studying how life adapts to lunar gravity. It reduces the need to constantly ship everything from Earth, but the environment is incredibly challenging.
How so?
You've got near-perfect vacuum, gravity that's only 1/6 of Earth's, and those extreme temperature swings between the long lunar day and the equally long, incredibly cold lunar night each lasts about 14 Earth days.
That sounds tough to live in. How do we make it work? This idea of using lunar resources, ISRU.
In situ resource utilization, it's absolutely key. We have to learn to live off the land.
So what's actually there to use?
Quite a bit, potentially. First, there's regolith, the powdery soil everywhere. It's abrasive, but you can use it.
For building, radiation shielding.
Both. Then you have minerals. Lots of silicates, oxides containing metals like iron, titanium, aluminum, even traces of rarer elements.
And water. That seems crucial.
Water ice, that's the big prize. We think there could be significant amounts frozen in permanently shadowed craters near the poles mixed in with the soil. Maybe billions of kilograms in the top meter or so. Even outside the poles, samples show small amounts of water bound in minerals.
So ice mining at the poles.
That's a major focus. There are also volatiles like hydrogen, helium, including the rare helium-3 implanted in the regolith by the solar wind, and of course abundant solar energy, especially near the poles where some areas get almost constant sunlight.
Okay, so the raw materials are there. How do you turn regolith and ice into, say, breathable air or building blocks? That sounds like serious engineering.
It is. For water, you could potentially heat the icy soil in those shadowed craters, maybe using reflected sunlight, and trap the vapor. Or, more widely applicable, use hydrogen, which you can also get from the regolith, to react with metal oxides like ilmenite to produce water.
Creating water from rocks.
Essentially, yes. And that water gives you oxygen to breathe and hydrogen for rocket fuel. You can also extract oxygen directly from the regolith itself, using processes like electrolysis on molten soil.
So you can bake air out of the ground.
In a manner of speaking, for materials you can extract silicon for solar cells, metals for manufacturing, even make strong basalt fibers from melted regolith for construction composites.
And building. Are we talking lunar bricks?
More like 3D printing. Using robots and techniques like solar sintering, using focused sunlight to fuse regolith particles together, you could print landing pads, roads, habitats, radiation shielding.
Layer by layer.
Exactly. Or use inflatable structures, then cover them with thick layers of regolith for protection. And using natural lava tubes, these big underground caves would be ideal instant shielding.
That makes sense. But what about power? Especially during that 14-day night. Solar panels won't work then.
That's where nuclear power comes in. For a permanent, reliable base, especially one needing lots of power for ISRU, a small nuclear fission reactor is likely essential.
Nuclear power on the moon?
NASA's already working on it, the Fission Surface Power Project. They aim to land a small, pre-assembled reactor, maybe 40 kilowatts or more, in the early 2030s. It offers constant power, day or night, regardless of sunlight. That's a game changer for long-term survival and operations.
And life support. Growing food.
That's also advancing. Developing closed-loop systems that recycle air and water, like Europe's Melissa project. And we've seen experiments, like China's Tianji 4 sprouting a cotton seed on the moon. Early days, but promising.
So the Artemis base camp at the South Pole?
Yeah.
What's the vision?
Think of a hub of activity near resources like water ice, landing pads, habitats, maybe a rover garage, power systems, science instruments, a place for crews to stay for longer durations, conduct research, explore. The polar location is also great for some types of astronomy.
It sounds like a real outpost. But who owns what? You mentioned the treaties.
Yeah, that's a complex area. The Outer Space Treaty says no nation can claim sovereignty. But how do you manage resource extraction? The Artemis Accord set guidelines for cooperation and safety among participants. China is leading its own initiative, the International Lunar Research Station. Coordination will be key.
It seems like we're really on the cusp of making this happen,
Yeah.
which leads to the biggest question, perhaps.
Hmm.
Does having a base, a spaceport on the moon, really open up the rest of space?
Mhm.
Is it the stepping stone people talk about?
I think it absolutely is. There are huge strategic advantages compared to, say, just building bigger space stations in Earth orbit.
Like what?
Well, first, gravity. Even 1/6 G is better for human health long-term than 0 G. Less bone loss, muscle wasting.
That's a big plus for astronauts.
Huge. Second, the launch advantage. It takes way less energy to launch from the moon than from Earth because of the lower gravity. You could potentially build and launch large interplanetary spacecraft from the moon much more easily,
Build them there.
using lunar materials. Third, fuel production, using that lunar water ice to make rocket propellant, liquid oxygen, liquid hydrogen right there on the moon.
Means you don't have to haul it all the way from Earth.
Exactly. That's a massive saving in mass and cost for deep space missions, like going to Mars. You fuel up at the lunar gas station. Fourth, protection. You can easily shield a lunar base with regolith or build it underground in lava tubes, offering much better protection from radiation and micrometeorites than an orbital station.
Safer for long stays.
Definitely. Fifth, it's a strategic hub. A base camp, the gateway orbit. It creates a logistics point, a port for missions venturing further out. Think of a cislunar highway system.
And finally,
It's a learning experience.
Why?
We learn how to live and work long-term on another world, develop the technologies, figure out the operations needed for even harder destinations like Mars. It's the perfect proving ground.
so combining all that,
Yeah.
it really does sound like the foundation for becoming a multi-planet species.
It lays the groundwork for a sustainable lunar economy, yes, and dramatically lowers the barriers to exploring the rest of the solar system. It makes those grander visions seem much more achievable.
What an incredible journey we've covered. From that violent birth billions of years ago, to the moon stabilizing Earth, guiding early explorers, welcoming Apollo astronauts, and now this vision of bustling bases and spaceports.
It really spans the cosmic and the human scale. We went from looking up in wonder to leaving footprints, are now planning to stay.
We've unpacked the theories, the evidence, the missions past, present, and future, and explored how ISRU and technologies like nuclear power could make a lunar outpost a reality, serving as that vital springboard.
And if you think about the bigger picture, establishing ourselves on the moon isn't just about planting flags again. It's about fundamentally changing humanity's relationship with space.
Expanding our horizons.
Truly expanding them. It tests our ingenuity, pushes our technology, and forces us to cooperate on the global scale. It really makes you think. Once we are living and working there routinely, what unforeseen discoveries, what new challenges, what completely new ways of thinking might emerge from having that off-world perspective, that's the really exciting part.